Woohoo! And here we go. Chapter 3, the dynamic Earth. Specifically today, we're going to look at the geosphere. Now this section is broken up into an A and a B. I'm going to go through it all in one video, but when it comes to notes, it'll be two sets of Cornell notes. So we have a essential question, and later I'll bring up the B one. We cover a lot of ground here, so hang on. I'm going to run straight through it. If you need to pause, obviously go ahead. But with no further ado, here we go. Your essential question is, describe the composition and the structure of the Earth. When we get to it, we talk about the structure and we talk about the composition. There are two separate ways of looking at it. Make sure you can keep them straight in your head. The Earth as a system. This first little bit is sort of talking about the entire chapter in a quick summary, so here we go. The Earth is an integrated system. Scientists divided the system into four broad parts: the geosphere, rock; the atmosphere, air or gases; the hydrosphere, water; and the biosphere, all the living things. These are our very simple basics. If you look at the picture I'm throwing up here, let's look at where we find these and the relative sizes. Now, I'm not going to nitpick you on the distances, but in general, you should have an idea. On the Earth itself, the little pie or wedge shape, we're looking at from the ground all the way down to the core. That's some 6,378 kilometers deep. Then when we get to the top, if we talk about the atmosphere, still on that kind of wedge shape, the atmosphere can go 1,000 kilometers up. Now that's everything in counting our atmosphere. That's not most of where you and I and living things are. When it comes to the hydrosphere, water, well, we got to go down to the very deepest trench, the Marianas Trench in the ocean, and all the way up to where there's no more water vapor, which pretty much ends at the troposphere, maybe a bit into the stratosphere. But that's only a total of about 29 kilometers from the very bottom to the top. And then the biosphere itself, we only have oxygen breathable up about 5 miles high. We really like top of Mount Everest, say, and we really don't have very many living things hitting that area. So about 29 kilometers. It's about 9 kilometers of that is above water, and we have 11 kilometers of ocean below that. So the biosphere is only a total of about 20 kilometers, the hydrosphere about 29 kilometers. Just a rough where these things are and how they exist. Now remember, environmental science is an interdisciplinary science. We have to know something about all of the sciences so we can tie them in together. So this chapter is going to be a real quick run through of your Earth space, if you will, which probably took months to cover in middle school, and we're going to go through it in a couple of weeks here. So this should all primarily be review. Let's dig in. The Earth as a system, the geosphere. Mostly it's a solid rocky part. It extends from the center of the Earth, the core, all the way up through the mantle and into the crust where we live. The atmosphere is that mixture of gases that make up the air that we breathe, and it goes on beyond where we can actually breathe as well. And most of these gases are really found in the first 30 kilometers. The picture we saw before said about 29, but no more than 30 kilometers, about 18 miles up, and you're out of any kind of atmosphere. The hydrosphere is just making up all the water on or near the surface. It's going to include stuff in the clouds. Mainly we're talking about oceans, lakes, rivers, etc. Most of it is obviously in the oceans, covers about 3/4. I think the actual number is like 71%, but it's also found in the atmosphere, on the land, and down in the soil, like our aquifer, or some is sitting there where the plants are pulling it out. Then we want to talk about the biosphere. Now the biosphere is mixed into all of this somewhere, but it's a fairly thin layer. maybe about 9 kilometers above the Earth's surface. Once again, not very much going to be above the 8-kilometer mark, but down to the very bottom of the ocean. And kind of the same thing. We talk about the very bottom of the ocean. It doesn't have a lot of life per square kilometer, but it's very big, so we do find life. So it is made up of parts of the geosphere, the atmosphere, and the hydrosphere, and the biosphere making that fourth one. But we find the biosphere throughout all of it because life finds a way if there's a niche that it can trench itself into. And we get asked a question a lot, well, how do we know there's a core? How do we know there's a mantle? Because we've never been there. We have never drilled beyond the crust. We have never reached the mantle, the layer right below the crust, so how do we know it's there? How do we know the core is this? Well, the same way we know it's windy outside by looking at the trees. We can't see the wind, we can't see the air, but we can see effects of it. We can do tests on things we can't always see and have a pretty good solid idea what it is. If I open my refrigerator and it stinks, I don't have to see that something's gone bad. I know something has gone bad in the fridge. Then I use my other senses to try and eventually find it. So we don't have to see something to know it exists. But we run experiments. And one of these is we use seismic waves, like in an earthquake. When an earthquake occurs, we pay attention. Those waves travel, the energy just like ripples on a pond. If you drop a rock, you can note how long it takes the ripple to make it across the lake. But if something's in the way of the ripple changes direction and can change speed. And that's what we do. As these waves travel through the interior, we can detect what they're doing, and it gets altered. So if we look at the picture here, a wave occurs, and we're looking at two different types, but if we pay attention to the kind of that yellow or green that are going out like this, well, we can measure if it started here, how fast they're traveling, and it should reach the other side of the earth by such and such time. And what we find in areas that are skirting the core, it reaches it at a predictable time. But if I get down here, it gets there a little quicker. Well, why did it get there quicker? It had to pass through some different material. We have the lithosphere at the top, very hard, and as it hits the mantle, it's a different density, and as it hits the outer core, that is a different density, and metals tend to vibrate at a faster speed, so the waves speed up. When it hits the inner core, this is solid. The outer core is liquid, the inner core is solid, and it speeds up again. So we're showing by those, goes from it, the shape changes, and it alters. So we can track the speed of the waves and therefore determine what it must be hitting and when. So our experimenting with the seismic waves and timing when they reach different parts of the earth allows us to get a pretty good picture of what must be inside of the earth. We're going to talk about the composition of the earth. Remember your essential question, the composition versus the structure. Composition. Composition are the three parts: crust, mantle, core. That's it. These layers are made up of progressively denser material. So the crust, not very dense. The mantle, denser. The core, densest. They get progressively denser as we go in. The crust right at the top, this is your vocabulary term, outermost layer right above the mantle. It makes less than 1% of the entire planet's mass. Somewhere between 5 kilometers to 8 kilometers thick below the ocean, because the ocean's taking up space, and between 20 to 70 kilometers thick beneath the continents. Say in Florida, we're fairly low, it might be more like 20 kilometers. In the Himalayas or Rockies where you're up into some mountains, well, it might be thicker. It varies in its thickness around the planet. So if we start under the ocean, thinner. If we were to start trying to dig from the mountains, obviously we have a lot farther range to go. Below this is the mantle. So the crust at the top, thinnest and the least dense material. The mantle is a layer of rock between the core and the crust. It's a medium density, we say, makes about 64% of the mass of the planet. So it's kind of our big chunk of it. And then it takes us down to the core. The mantle is rock, denser, and this rock is going to go from being kind of a almost liquidy near the core to fairly solid and dense. Remember, everything can be a solid, liquid, or a gas, including rock. So the mantle is going to vary depending on how close it is to the hotter parts of the core. So we go from crust, mantle, core, least dense, medium density, most dense composition. Now we want to talk about the structure of the Earth. When we talk about the structure, we're going to talk about its physical properties. We base it on different physical properties, and it gets broken down into 5 layers. The lithosphere is the very top. It's the solid outer layer of the Earth, and it consists of the crust and the very rigid upper part of the mantle. The lithosphere is this hard rock layer, the crust, and a tiny bit of the top of the mantle. It is a cool, rigid layer. So this is its structure. It's cool, rigid, between 15 kilometers down to 300 kilometers. So it's going to include part of the mantle, that part of the mantle which is going to be hard rocks. Remember, the mantle sort of changes. The crust is always solid, the mantle is lithosphere, the top cool part, and this is where it is divided into the tectonic plates. The tectonic plates are the lithosphere sitting on top of the next layer. The tectonic plates sit on top of the asthenosphere. The asthenosphere is the solid, pliable layer. Think kind of like icing. You know, it's kind of solid, but if you touch it, you can mush into it. So it's kind of a soft solid, if you will. It's pliable. You can push into it and it can rebound a little bit, or you can push your finger all the way through it. Play-Doh might be a good example of this. It's kind of like a solid, but you can push your finger all the way through it pretty easily, unlike a rock, which is very rigid. So it's a pliable layer. This mantle part flows very slowly, which is what allows the tectonic plates to float on top of it. That's the asthenosphere. Below the asthenosphere is the mesosphere, and this is the lower part of the mantle. And more of this is going to be sort of true magma type rock. It's going to be more liquidy. And that takes us to the outer core, which is a dense liquid layer. And at the very center of the Earth is a inner core, which is going to be solid, and we believe it's made up mainly of iron and nickel. Why do we think it's made up of that? Our magnetic field around the Earth. If we have a hot iron nickel substance spinning, this is one way we can create a magnetic field. So because of our magnetic field, we feel pretty confident of what that core must consist of. Now, the core is estimated to be anywhere between 4,000 and 5,400 degrees Celsius, but it's solid because it's under enormous pressure. All the rock and planet is sitting on top of it. It's under such a high pressure, it cannot be a liquid. So solid, liquid, liquidy, pliable, solid rock. If we look at the picture here, it just kind of takes us through that in those things. So this is the structure, and it's based on its physical properties. I'm going to start at the core. Solid metal, liquid metal, the outer core. The mesosphere is going to be primarily like magma, molten-ish rock. The asthenosphere is going to be a pliable, kind of like Play-Doh, a little bit in between a solid and liquidy. And then the lithosphere at the top is going to be a hard crust, hard, thin rock layer. So that is the structure of the Earth in looking at it compared to its composition. This takes us to section 1B, where we're going to talk about the geosphere. But your essential question, once again, second set of Cornell notes at this point, wrap up the first section. Your essential question: what is the driving force behind both earthquakes and volcanoes? Diving right in, we're going to talk about the plate tectonics. Now, we referenced them loosely before, that the lithosphere were where we find the plate tectonics. The tectonic plate is just a chunk of lithosphere. It's going to consist of crust and a little bit of that hard, rigid part of the mantle, and they glide across the asthenosphere, that thin, pliable layer. And our continents are located on the tectonic plate, so our continents move around with them. And obviously, we have tectonic plates that move through some of our continents where we are. Like in California, we have a big fault line, and California is on one side of the fault line, or parts of California, and the rest of the United States are on the other fault line. But our big continents sit on top of these huge tectonic plates. Now, the major plates in general include the Pacific, the North American, South American, African plate, the Eurasian, and the Antarctic plate. There are a lot of minor plates. When we look at some different pictures and they show the fault lines or plate lines, these are the major plates. There are some minor ones as well. Earthquakes. Key term, earthquakes. When we measure the magnitude of an earthquake, or we measure the energy released by an earthquake, we refer to that as magnitude. Now, the smallest magnitude earthquake that can be felt is a 2.0. And the biggest magnitude we've ever recorded is a 9.5. Anything over 7.0 causes major damage. Where I grew up in South Carolina, we lived on a minor fault line, and we had earthquakes up there, actually quite a lot. But I only remember feeling 2 of them. And in both instances, at the time, I thought my eyes were looking fuzzy because I was looking at the TV because it vibrated slightly. And it was only later when they said, oh, an earthquake hit, blah, blah, blah. It was a 4 something. Both of the ones that I felt were 4. We had very small ones, like I never felt a 3. I guess if you're right at the epicenter, but very, very minor, only a very slight shaking, like a truck driving by your house, something of this nature. But 7 and above, major damage. Each increase in a whole number from magnitude 1 to 2, 2 to 3, 3 to 4, etc., indicates a release of 30 times more energy. So a 6 to a 7, it releases 30 times more energy than a 6. So we usually tell it was a 6.3. We have it scaled from 6.1, 0.2, etc. because it's a huge amount of energy. The difference in a 6 and a 7 can be catastrophic in its difference of damage. So each number up, 30 times more powerful. The picture we have here is where earthquakes occur. They're along these major fault lines. Now, we have the North American and South American kind of almost in the center. It's a little bit off center. And all the little red dots indicate earthquakes over, I'm not exactly sure from this picture, probably the last 100 years, could be the last couple of 100 years, where we've detailed they're happening. And they tend to happen primarily along these major fault lines. We see some off in areas where we don't have one of these major lines, and in most cases, not all, this is associated with some of the minor fault lines. But as you can see, along these major fault lines, that's where we tend to get our earthquakes, which takes us to volcanoes. Now, a volcano is just a mountain that is built out of magma. So a fissure opens up in the earth, or a hot spot, and the magma pulls up from the earth and it spews out, cools off, spews out, cools off. And I have a mountain, which is a volcano. Now, many volcanoes will lay dormant for years and years because it seals off, the pressure builds, and eventually it releases again. It rises up from the Earth's interior all the way up to the surface. And volcanoes are often, not shockingly, found either where they collide or pull apart. Now, some plates are pulling apart and then the magma can kind of leak up. Our mid-oceanic ridge is largely formed by it's pulling apart, magma pushes up, so we get a mountain range down there. But it also occurs where they push and slide together because we'll get fissures opening up where magma can move up from it. So they tend to be near these plate tectonic boundaries. And the majority of our active volcanoes are in this area that we refer to as the Ring of Fire, right around the fault lines around the Pacific Ocean. We tend to get more there than anywhere else. But you can notice in some of these other areas, dipping down around Asia there, we have volcanoes in other places than just this Ring of Fire. But it just has a very strong preponderance of volcanoes erupting around it. Now, some of the global effects of volcanic eruptions. When a volcano erupts, it can actually change Earth's climate for several years. A volcano erupts and it releases a huge ash cloud. Now, in this ash cloud, we'll have sulfur in it, carbon dioxide is in here, some nitrous oxide, and all these gases release up into the atmosphere. For the most part, the main change they do is this sulfur-rich gas reaches up into the upper atmosphere, and then it begins to spread across the planet because of our global wind patterns. It gets up high and the wind begins to disrupt it, and we have these really fine particles up in the sky, and it makes what we call a bright haze. So the sunlight coming through this atmosphere hits these little particles, and little bits of sunlight get reflected and blocked, and they don't make it all the way down to the planet. More of the sun's radiation is getting reflected and absorbed by these particles and gets re-radiated back into space and doesn't make it down to Earth. So it can cause a cooling of the entire planet for a few years. Now, as a general rule, we're only talking a degree or so. But when we're trying to track things like global warming and climate change, we have to look at all of these factors and say, oh yeah, but the temperature's been going down this last year or two. Well, if we've had a large volcanic eruption, yes, you're correct, but it's not because it's stopped, it's because of another factor. So it's important to try and look at all of this when we make decisions. And lastly, we're going to talk about erosion as something that affects on the planet Earth. Now, the Earth's surface is constantly battered by wind, running water, and both of these things can move rocks around and change the appearance of the Earth. We can also have chemical weathering. Chemical weathering is where the different materials get loosened and dissolved or worn away. Acid rain is one. The rain gets acidic. Now, not so much it burns your nice skin off, but enough that when it hits rocks, it can begin to dissolve them over time. And this is known as chemical weathering. Physical weathering is just the rain hitting it and causing some of the bits to break off. But if the rain hits it and the rain begins to have a chemical reaction with the rock, causing it to dissolve, that's chemical weathering. But either way, erosion is just going to take the materials from one place and move them somewhere else. It wears down rocks, make them smoother over time. It can smooth down entire mountains, cut out valleys like the Grand Canyon. All of these just come from erosion. Now, for the most part, we're talking about three: water erosion, wind erosion, and chemical weathering or chemical erosion. But of these, water is king. Rivers and oceans produce dramatic changes on the Earth's surface. The tides changing the shape of things. North Carolina's outer banks are constantly shifting and moving because of the ocean tides and currents. Waves from storms can completely make a shoreline look different in a matter of days. And obviously rivers over time, carbon gorges like our Grand Canyon. Lastly is wind erosion. Now, in places where very few plants grow, like deserts or the sandy areas like beaches, then wind can blow soil away very quickly. A sandstorm comes up in Saudi Arabia, and the landscape changes once again practically overnight, picking up sand here and dropping it over there. The wind does have a big factor in erosion, but primarily places where there's not a lot of plants. And obviously soft rocks like sandstone are much more likely to get weathered. We see this out in the Midwest, as opposed to rocks such as granite, which is pretty hard for wind to have much of an effect of granite. That wraps it up for this one. Take care, and we'll see you next time when we look at section 2.